When you conduct a hypothesis test, you conclude by either saying that there's enough evidence to reject the null hypothesis or saying that there is not enough evidence to reject the null hypothesis. Of course, either of those decisions could be wrong, and so now we're going to briefly touch on different types of error before we move on to thinking about what happens when the assumptions behind tests are not true. Type 1 error, by definition, is the error you make when you reject the null hypothesis when actually the null hypothesis was true. So the truth is that there's nothing going on, but you've decided to reject the null hypothesis because your p-value is less than whatever arbitrary cutoff you've selected. A type 2 error, by definition, is when the null hypothesis is false. There actually is something going on in the population, but you failed to pick it up. You failed to notice that. You don't have enough evidence to reject the null hypothesis when you should have. Relatedly, power is the probability that you reject the null when that is what you should do. So it is 1 minus the type 2 error. Assuming the null hypothesis is false and there's actually something specific going on, there's a certain truth, the parameter is equal to a certain value, the power is the probability that you correctly notice that and reject the null hypothesis. What we're going to move on to now is what happens to t-tests when the assumptions are false. Not all assumptions are created equal, as it turns out. One of the assumptions underlying t-tests is independence, and we'll touch briefly on this one. We'll talk a lot about normality, and it turns out normality doesn't just mean that the distributions are normal, it also has to do with whether two different populations have the same shape, so whether their sample sizes are similar, or whether they're outliers, and we'll talk about all of those. And then there's also equality of variance. If you're going to do a t-test with pooled variance, there's this additional assumption that the variances are equal in the two populations. Turns out that has to do with sample size. Here are two terms that we'll use. Robustness means that a procedure, such as a t-test, still works, even if the assumption isn't true. So we have a procedure that's robust to an assumption if the procedure works regardless of whether the assumption is true. Very similarly, a procedure is resistant if the answer you get is the same if you change a small part of the data. So if you all of a sudden have an outlier, the overall answer won't be influenced if a procedure is resistant. The first assumption to touch on is independence. So why might you have a lack of independence? Maybe there are subgroups of units that are similar to each other. You tried to do a simple random sample, but actually you got clusters of people, so every time you selected a particular person, you also got that person's family. So now you don't have independence. Or maybe units vary over time. So as you collected data, patterns change day to day, and so units are correlated with other units collected on close days. Or similarly, maybe the units are related to each other across space. You measured a bunch of animals across a field, and animals who are close to each other in terms of where they are in that field might be more similar to each other, might be correlated with each other. In all of these situations, the standard error calculations, the denominator in our t-statistic, is just wrong, and you need more advanced calculations. We don't have a magic solution here. So if the independence assumption is broken, you need to stop and find a better method. So how do we figure out whether the independence assumption is met? This is not, there's no test for this. You think carefully about how the data was collected. Is there a reason to suspect you might have clustering or variation over time or variation over space? Sometimes graphics can be helpful, but most often thinking about the independence assumption really is just thinking. And when the assumption of independence is violated, what do? You use a different method with standard errors that are calculated in a better way. So I said that you can check for independence graphically sometimes. Suppose that you know that your data came in two batches, batch 1 and batch 2, and you're wondering if you have some kind of clustering effect. You could make box plots of the data in batch 1 and batch 2, and here we have a picture where it's clear that although this is the overall data set, units within batches are pretty correlated with each other. If you're in batch 1, I know you're most likely going to have a higher value. And so I would want to take those clusters into account and not use a procedure that assumed independence and ignored those batches. Similarly, perhaps I have a data set where the rows are ordered in the order that they were collected. So the rows go down in terms of time. If I plot my data points against time and I see a pattern like this, I know that time matters. it's not that the data was sampled randomly without regard for time. And so I'd want to use a method that's appropriate for that.